You can hear me okay? So I'm very happy to be here. Thank you very much for the invitation. And it's kind of my privilege to talk about work which was, in the most part, done by the two PhD students. So Vytautas and Federico are lurking somewhere here. If you ask questions which are too difficult, then I'll send you to them. So the talk is about Rust. We're interested in verifying something about Rust programs. So let's start with a completely different language. So imagine we have this little snippet of C. So I'm kind of assuming everyone might have seen C at some stage, for better or worse. And the idea here is we have some code. It takes two pointers to linked lists in the heap. And now we do something super simple. So we save the length of one list into an integer. Then we append the value to the second list, the first list, I guess. And then we check that the length is still the same. And we're interested in verifying functional properties, usually of a more interesting kind than this one, but this will do as an example. And already there are many things that can go wrong. So what could be wrong with this code? Well, one thing is whether this property holds or not depends on whether we even get to this program point. So it could be that the program already crashed. Maybe B was null, okay? Then, of course, the question is kind of meaningless. It could also be that these two lists on the heap overlap in some way. Maybe A and B are aliases to the same list. Maybe A and B alias somewhere inside their own structure. Then it's not so clear that this length property is going to hold anymore. And of course, these days, almost all software is concurrent. I mean, if there's some kind of data race and some thread is coming in and playing with these lists as the code executes, I mean, somehow all bets are off, right? Who knows whether this assertion holds or not. So we're kind of stuck on very basic properties, even for a tiny bit of code, and this is kind of a known issue, right? That we're not the first to observe this. So there are many verification techniques that set about to solve this problem, and many come from the formal methods community to allow you to do modular proofs about these kinds of programs. Most famously, separation logic, and Hongsop was there at its inception, very influential at the time. There are several other logics, and they, broadly speaking, give you a handle on this kind of problem in the following ways. So firstly, they give you some notion of ownership or permissions, some way of prescribing which parts of the program state a certain piece of code is going to access. And then you have to lift this in some way to unbounded parts of the heap. So you have some way to describe data structures, in this case lists, by, say, user-defined predicates in the logics themselves. And then what you need is some way to describe the memory. So you might say, well, there are two lists, and you want to be able to say something like, these two lists are disjoint in memory. I know that they don't touch each other in any way. And then in practice, if you want to implement this kind of reasoning in a tool, typically you have to do a certain amount of work. Okay, also on paper, you have to do a certain amount of work. So for example, unrolling these list definitions and peeking inside and seeing which fields are actually there, this requires additional annotations. So this is kind of a very high-level view of what it is to take a modern program logic and try to start tackling this problem. And I guess a reasonable question is, what is this like to use? So I'll stick with my not using any Rust in my Rust talk for the moment. So I'm going to show you, is this readable at the back? So this is a tiny snippet of code which appends a value on the end of the list. So you could imagine this is some abstraction of this append method that I had. The language is Viper, which is set up for doing these kinds of proofs. And Viper is very close to my heart, but this is also not a talk about Viper, and I'm not going to tell you too much about it. I just want to give you a feeling for what's involved. So here is the code. It just does the usual thing. So you check whether we're at the end of the list. If we are, we allocate some new node with the right values stored in it. And if not, then we recursively call append. And Viper is already unhappy because part of the methodology of these kinds of logics say you're not allowed to just play with the heap when you like. You have to show that you're the one who has the access to do so at the moment. So I can try to fix this problem by adding something like a precondition. And I'll say, well, I have the access to this a.next field. But this doesn't really solve the problem, because now on the recursive call, it says, but how do you know you can call a.next or next, which the next call requires? So this is no good. And what do we do instead? Well, now we have to set about with these predicates. So we can define a predicate which describes a linked list by saying, well, that gives you the access to the next field of the list, and the access to the val field of the list. And if the next field is not null, then there's some recursive instance of the same predicate. So now I have a way of talking about entire linked lists in the heap. and I can make my precondition something that says I've got a list at A. And this doesn't work because I've got lurking here a copy of the same definition, and Viper isn't happy with having copies. So now this still doesn't work. Well, why is that? I've got my list at A, so I'm not allowed to read this field for some reason. It turns out you have to write some additional annotation. So you have to tell the verifier, peek inside this predicate, see that you'll find this field as you need it. And now, wait, now why does this verify? Ah, because I haven't said that I'm giving the list back. So I want to say at least I have a list at the very end. And now it doesn't understand why I have a list at the end, and this is because I have to do the kind of dual annotation, so I have to say, well, fold this definition back up. And then it says, I'm still not sure why this is the case, and it turns out, well, I've also got to fold the same definition after I allocate the new object. Ah, I see I've made a typo. So this is what I want to... Ha, that's good, I even made a mistake. What I want to get across here is kind of a feeling for what it takes, which I'm not successfully achieving live, what it takes to do these kinds of proofs. Okay, it's done. Oh well. So you need to have this kind of additional logical layer. You define your own definitions. These are recursive. You do a certain amount of annotation. And we can prove something about the code, but actually so far I didn't even prove anything very interesting, right? I haven't even proved that append didn't append. So I did all this work just to persuade the underlying methodology that my way of playing with the heap sort of follows the rules. And you can prove much more interesting things in Viper. I won't go into that. If you're interested in that, then see me afterwards. In particular, I can certainly use Viper to prove the same example, and actually it's lurking here, right? So I can prove some kind of client code like the one that I showed. But the kind of high-level message, if I go back to where I am, is, now imagine you apply this to some serious code. So this isn't even that many lines of code, right, compared to many of the talks we've talked about today. And you're going to start writing these annotations all over the place, right? So somehow you need to define all of the data structures involved. You need to specify the functions everywhere. You need to write all the annotations. This is fine. This is like powerful stuff. But it's clear that you have to be a verification expert to get anywhere with this kind of methodology. And all of the work that I showed you so far is kind of mandatory. It doesn't matter how much I'm interested in proving about my program, whether I care just about crash freedom or whether I need a full functional correctness proof. I have to do all of this work just to even get started. This is what I'll call for the rest of the talk the core proof. So somehow just the amount of work you need to apply one of these proof techniques to prove any property about a program. And this is non-trivial. So we got interested in Rust because Rust has a different model for the programmers when they're writing this kind of code. So this is the same example as I showed at the beginning, but written in Rust. And there are a few syntactic differences, and the most important difference is the type system is different. So Rust has a meaning to types that by default says this is a unique owning reference to the underlying memory. So now, if I go back to the issues that I was talking about before, the crash that could have happened here can't happen anymore in Rust because Rust builds into the type system that if you have reference to the memory is definitely allocated, there's definitely a value there. In particular, it's not null. Null is handled with option types in Rust. The kinds of memory errors therefore go away. The aliasing problem is also controlled. This says that A and B can't be the same, and not only can they not be the same, but they can't overlap anywhere transitively in memory. And data race freedom is also guaranteed because the same rules apply when you spread out the ownership of the memory between different threads. The fact that I have ownership implies there are no threads concurrently running that can possibly be touching this part of the state. So now Rust takes away a lot of the annoying problems for the programmer, and the question we asked is, can we somehow exploit this type system for verification? If you want to prove something about your program, shouldn't that make life easier again? So what would I like ideally? Let me show you a different tool. So here is the same code written in Rust, and I would like a tool, and I'd like to be able to hit a button, and the tool tells me, after a few seconds, the tool tells me, oh, I don't believe your assertion holds. Can anyone see why? If you don't see it now, you probably won't see it. So I made a typo when I copy-pasted from the slide, and the append was supposed to be on the first list and not the second. So now I run the example again, and now verification succeeds. So what is going on here? Well, somewhere behind the scenes, we're constructing this fancy formal proof, but we don't see it at the source level anymore. Let me go to a different version of the same example, where I filled in a bit more specification. So suppose I'm interested in proving something a bit more interesting about the program. And here I went for the idea that if the list A is sorted and under certain conditions about inserting 100 on the end, then the list will be sorted at the end. Let me show you a little bit more. So this is all Rust code. The only thing that's not Rust is anything you see a hash in front of. These are the annotations that our tool understands. So here I have a length function. The length just computes the length of the underlying list. The pattern matching syntax is probably familiar to many people. This sum box ref tail is a little bit on the heavy side, but that's just what it takes to go through the options and the boxing that I have in the particular structure. So this computes the length in the obvious way. Now I thought I would quickly write, just to show you a little bit more Rust, I would quickly write a get function for my list. So what does get do? It takes a reference to a list and an index, and it's going to give me back the underlying value in the list. So I'm going to start with, if I'm at the right position, if index is 0, well then I'll just return the value that's stored here. And otherwise, what should I do? Well, I'm going to match the next, and if it's, and here we have to get the slightly fiddly parts right, but still, if it's some box ref of some tail in the list, well then I'm going to recursively call my get, and I'll pass, so I'll call it on tail, and I'll pass index -1. Now this isn't allowed because I haven't given a, wait, why is this not?
Close the bracket on line 44. Open the bracket, but you don't close it.
Oh, thank you very much. Yes, you're quite right. Doesn't even pass. Okay. So here the Rust compiler is telling me this code is no good because I didn't write a none case. So I have an option type here, could be the end of the list. What do I want to write with none? Well, somehow this shouldn't happen. Right? This means that my index ran off the end of the list. So I'm going to claim that it doesn't happen, and in Rust you have this unreachable statement which basically crashes if it happens. This is like assert false. So now Prusti, our tool, is complaining instead that this unreachable statement might actually be reachable. Well, that's kind of reasonable. I shouldn't really call this in totally arbitrary ways. What I should do is make sure that I call it with an index that is within the bounds. And so here I'm writing a precondition on the function, which is going to be used by a verifier. Note that the precondition involves code. So I'm calling the length function in the precondition.
Index greater equals to.
Thank you. Now this verification succeeds. I think, let me just do one more because it's more fun.
Is that spec inductive, and that's why you use it as a procedure summary, or?
Yes, exactly. So every call to a function is being reasoned about in terms of its specification and nothing else. Well, it's type signature and its specification. I'm going to write what it means to be sorted, and it turns out that's a little bit easier. So if I've got a no next field, then the list is sorted. And if I've got some box ref something at the end of the list, then what do I need? I need that this self's value is, let's say it's ascending order, less than or equal to tail's value, and tail is sorted. You may have noticed this pure annotation lurking here. Pure is just a way of telling our tool you can use this function in contracts. You can use it in specifications. In particular, it's not supposed to have any side effects. So now, what fails now? Huh. It's not quite what I expected, unfortunately. I was quite happy with my sorted definition. Failing assertion is this one, line 41. it doesn't know that when I call get, I'm living up to my own precondition. My index is... Aha. That's very interesting. I guess my a.len minus 1, yeah. Oh. Okay, I might just close this demo at this point. Unless anyone who's more knowledgeable knows what went wrong. I'm a bit surprised because I was fairly convinced that I've done all the right things here. Okay, I'll come back to this. It will come to me, but not live, obviously. So what I would like is basically a tool like the one I showed you. I mean, I'd like to get the specification right, but that's almost certainly my fault and not the tools. I've just probably missed something that I don't see right now. So we have this tool designed called Prusti, and what Prusti does is lift the type information that's available in Rust. So we plug into the Rust compiler. We rip out all the information that's there in terms of types, in terms of ownership, in terms of various static analyses that the compiler has already done. And now we take an input Rust program where optionally you can write specifications. So you can verify a program with no specifications at all. You can also choose in the tool whether you verify crash freedom, like that this unreachable line was actually reachable, and whether you prove other built-in properties like integer overflow doesn't happen. And now what we do is we feed via Prusti our Rust program with specifications into the tool, and it generates Viper code. And Viper is this verification infrastructure we have in our group for building these kinds of tools. And now we managed to spit out yes or no answers in terms of whether the code is actually correct or not. The nice thing is... Sorry, 1 second. Something... Okay, sorry. So let me tell you a little bit about the overall approach that we're implementing here. So we take the Rust type information. What we do is we feed this to our tool, and we generate this kind of ownership story and predicates that are necessary in order to write down this proof, like the one I showed you in Viper at the beginning. We take the signatures of the various functions, and we use these to generate pre- and post-conditions for those functions automatically behind the scenes. And then we take these compiler analyses that have already been done for us, including, say, borrow checking, which is a pretty fiddly notion in Rust. And we use this to generate auxiliary annotations that make the proof automatic, things like the fold and unfold statements that I had to write by hand at the beginning. And finally, if the user chose to add any specifications, which is optional, whatever they want to prove about their code, this gets mangled in a clever way, such that we're also proving this functional specification about the Rust program at the same time. And the idea is now this can be used by non-experts. So you remember I said, well, sadly, this is the situation. If you want to prove something using these techniques, you have to be super expert and you have to spend a lot of annotations. But what's cool now is that all of this is being done behind the scenes for free. So what the user does is they just write what they care about the code. They write the functional specifications. They can be minor, like I avoid overflows. They can be rich, like my search function actually does what it's supposed to. And the abstraction level is Rust expressions. You don't work in a custom logic, you work in a language which is essentially Rust. I want to tell you a little bit about what we're doing behind the scenes, so how we make this work, but I'm not going to go into super hairy detail. So I had my struct list in my example. So I mean, a list is basically a self with two fields. It has a val and a next field, and what we do is we generate a list predicate, like the one I wrote by hand, by reading off these fields and saying, well, certainly we have access to those locations on the heap, and we have this recursive definition of whatever type happens to be there. And these are also modeled as predicates. So basically every type at the Rust level becomes a new predicate at the Viper level that we generate in this way. And then we take a signature of our function, like the client one, and this ultimately says there are two lists and they're disjoint from one another in the sense of these permission logics, like separation logic. And we use this to read off a specification at the Viper level that it describes which permissions we actually hold. And then if the user comes along with the specification, we have ways of mixing that in, such that the specification is enriched with whatever properties they wrote by hand at the source level. So things are not quite as easy as that, and I just wanted to give you a hint of why there's an Uppsala paper about this. So it turns out in Rust you can do things much more difficult than I showed in this particular example, and one of the more challenging features to reason about is you have this possibility of what's called reborrowing. So you can pass a reference, in this case I said to some kind of tree, into a function, and now you traverse, maybe modify the tree in some way, and at some point you return a reference to a subtree. So what gets passed back to the caller is a reference somewhere inside this data structure, and now the caller is still allowed to mutate further if they want to. So now two problems arise for us. So from the caller's perspective, let me just finish telling you the rules. So from the caller's perspective, while they're still using this reference, this part of the data structure is effectively frozen. Rust will block you from using T that was passed in until this reference goes out of scope. When the reference goes out of scope, maybe after you've made some changes, it's as if that subtree gets inserted back in, and now the original becomes usable and mutable again. So from our perspective, we need to do two things. We need a way to explain at the Viper level, what does this tree with a hole mean? How do we describe a data structure where some of the permissions, some of the capabilities are missing because they belong to this other reference at the moment? And in terms of the specifications, which is more relevant for the users, they need a way of saying, what is the combined effect of, so I need to write a specification on get which allows a caller to know, in terms of changes they make to this subtree, what effect will that have on the tree as a whole? And what's particularly tricky about that is the get function doesn't know what those changes are going to be. It should not, right? We don't know how it's going to be used, and it's generic. But on the other hand, the client doesn't know the internals of the data structure, and the person this reference gets passed back to doesn't know in particular what path we took through the tree to reach this point. So writing a modular spec about this is tricky. To give you a flavor of what's going on, behind the scenes at the Viper level, what we're using is a separation logic feature called the magic wand. And the magic wand gives you a way of saying these kind of hypothetical, if you gave me back this part of the ownership, then I would have something that looks like this, these kinds of assertions. So we're generating proofs using magic wands, which requires yet more annotations behind the scenes. And in terms of the specification level, we designed a new concept called pledges, which I'll have to relegate to the Uppsala paper in case you'd like to take a look. So we evaluated what came out in two different ways. Firstly, we downloaded all the 500 most popular crates, and we put no specification on this code. We then filtered, because our tool does not yet support all of Rust, as you might expect. So it turned out we could support just over 20% of the functions. This is about 40,000 lines of code from these crates. And we wrote no specifications on these and nonetheless threw them through the tool to show that this underlying core proof always works. So we generate the fully elaborated proof that Viper can understand about how this ownership model that Rust type system kind of implies is to be explained as a formal proof. And this always works. It's about 1 million lines of Viper code, and about 10% of that are these kinds of annotations that one would otherwise write by hand. On the other hand, since we wanted to show the tool can actually be used to prove something about code, we took some neat examples. So we took this Rosetta Code's website, and that contains many sort of popular programming idioms, algorithms. So we took things like search algorithms and sorting algorithms, and what do we have in here, like this Langton's ant one. So they're relatively small but quite challenging snippets of code, and what's nice is you kind of know what they're supposed to do in advance. So then we wrote the formal specifications of various properties. That required a few more lines of code to get the specs through, and depending on how ambitious we were, that was more or less work. Then we ran it through the tool. I think the numbers are maybe a little bit small from the back, I'm sorry for that. Roughly speaking, it takes 5 to 20 seconds. For one or two of the examples which were rather more ambitious, it took about 2 minutes to run the verification. And we verified a range of properties. So in some cases, we just verified built-in properties, and then we verified other versions, usually sometimes of the same examples, in which we wrote something more like a functional spec. What's kind of neat is it turned out there were 2 bugs in these examples. So one was an integer overflow bug, and one was in the search function. It turns out if the value you're searching for is the very last element, then you don't get it. So that's something you would only find by trying to do the functional proof about what the algorithm is really supposed to do. I think I'll skip over the details there for the interest of time. So there's a paper. It will be presented by Federico next week. Will be at Uppsala. The paper gives the details of the encoding to Viper and also how we actually make this automation story always work. It describes this notion of pledges that we use to specify these reborrowing functions that I've hinted at. And it also defines more clearly which subset of Rust we currently support in this version of our tool. So, to conclude, I've shown you a little bit about this Prusti project that we're working on so far. And it gives a way of dramatically simplifying verification about these kinds of heap manipulating and potentially concurrent programs. What this will lead to, I believe, is a tool which can be potentially used by developers. They need not have a PhD in verification to benefit from some of these super cool techniques. There is a great deal more to work on. There are lots of features of Rust that we are hoping to address. Some language features like closures are hard to specify. Rust has this notion of unsafe code, which also makes life difficult. And we're on the lookout for more students. Certainly master's students are always very welcome. As Peter mentioned, I'll be moving to UBC, and I'm also hoping to hire PhD students. If anyone is interested in the topic, please get in touch. Thank you for your time.
Thank you. Okay, questions? Yeah.
Great talk. So what you did, like when you verified code without specification, that can be viewed as alternative way of testing Rust borrow checker. I'm curious, like, did you find any bugs in the borrow checker?
I don't believe so. Okay, they're shaking their heads too. Yeah, so in some sense, we're not checking that the borrow checker picks the best possible lifetimes or something like this, right? So the borrow checker gives us the lifetimes of the various references, and we check, in some sense, some kind of sanity check, indeed, that those make any sense in terms of the underlying memory safety proof. That was never wrong for the examples we looked at so far. Otherwise, indeed, Viper would complain.
Yeah. Do you want to?
Thank you for the presentation. I'm curious if basically Rust and the form Rust does proof during compile time and the math behind it motivated extensions for Viper. So basically you said Rust has some properties and you now need to extend Viper to support this.
Yeah, that's a very interesting question. So not so far, but in some ways, I think that will happen. So the thing is, we can make the encoding to Viper as kind of sneaky and clever as we like, right? This is kind of non-trivial in a sense, the way we're modeling what's going on in Rust. But so things like the magic wand support that we use were already there, fortunately. So many of the trickier features that we needed so far were supported. But we are considering an extension to Viper right now, essentially to allow chaining function calls on the heap together in a certain way. I'm not sure I can go into the details too much right now, but Viper is not so happy with you doing something like this reborrowing in Rust in the specifications themselves. But you need that if you want to say, oh, well, when you get this and read this field via 2 function calls, the value will be 42. So something like this reborrowing that you have in Rust needs to also be allowed in specifications. And it seems that will require some extension to what Viper currently allows. Thanks.
Okay, if there are no further questions, then let's thank Alex again. Thank you.